Hello everyone, welcome back to Technologies Discussion channel. For this video, I'd like to continue the discussion on RF mixer. Earlier on, I have described what is actually a mixer. Next, I also explain how a mixer actually works. Last but not least, on my previous video, I have also discussed the application of mixer. This video, I want to concentrate on the key parameters to describe RF mixer. For example, we have the conversion gain or the conversion loss. Next will be isolation. You probably need to know what is actually 1 dB compression point. Next will be the third order intercept point. Noise factor, dynamic range, which is the range that they are able to operate in a linear basis. And last but not least, intermodulation. So all this will be the objective of this video. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, I actually prefer you to ask me your question through the comment. Let me quickly explain the key purpose of RF mixer. Okay, so in fact, RF mixer is a 3-port. Okay, so this is a mixer. Okay, so this is the first port, second port, and third port. The first port is known as RF signal. So basically, this is the original signal that will be fed into the mixer. By properly control the LO, okay, we can actually ensure that a fixed IF frequency will be remain at the intermediate. Okay, so basically, this is actually the key purpose of mixer. Okay, basically, it will be used to convert RF power at one frequency. For example, okay, the power at the RF, it is used to convert into the power at another frequency. For this case here, will be the power at the intermediate frequency. Why we need to do this? We need to do this. We reduce from high frequency to lower frequency in order to make signal processing much more easier and also less expensive. Just imagine this, with higher frequency, you in fact need a higher frequency of amplifier, which will be more costly. And again, with proper control of LO, you can ensure that the intermediate frequency will be remain the same, and hence this amplifier is not required to work in a broadband so-called manner. So hence this actually make the processing easier and also less expensive. So this is actually the key purpose of RF mixer. Let me explain the first parameters of RF mixer, okay, which is the conversion gain or the conversion loss. Okay, so it actually depends, okay, whether after the conversion, whether it will be a gain or whether it will be a loss. So hence, either conversion gain or conversion loss. Let's take a look on this symbol of RF mixer in order to understand better. As I explained earlier on, a conversion is basically how efficient a mixer actually convert the energy from this frequency to the other so-called port at the other frequency. So this is a quick definition of mixer. Next, how to obtain a clear conversion loss. For example, for this case here, it will be the ratio of the input power. Okay, so this will be the input power. So hence, the input power will be at the RF, while the output power will be at the IF for a given LO power actually applied. So basically, with a given LO power applied, how efficient the power convert from RF to IF will be known as conversion gain or conversion loss. So typically for passive mixer, usually okay, they have conversion loss. While for active mixer, okay, which means that the mixer actually require a power to activate it. Hence, this may provide some form of gain. Hence, for this case here, they may be able to provide some form of conversion gain. So in short, why this is very important, conversion gain or conversion loss? Because it is directly impact the system sensitivity. So this is actually the first parameters of RF mixer, either conversion gain or conversion loss. Let's come to the second parameters of RF mixer, which is isolation, signal leakage between port. Let's come to the definition. Okay, so basically isolation is the amount of attenuation that is actually provided when a signal is applied to one port of a mixer and then basically they arrive at the other port. So this is a quick definition of isolation. Just imagine this, when I actually apply a very strong signal at the LO, okay, it may lead to the RF, it may also lead to the IF. So this is what we know as this LO to RF isolation, which means that if I put a very strong signal at the LO, it may lead to the RF, which means that the LO signal must be avoided that they actually appear on the antenna at the RF. On another situation, when I actually apply a signal at the LO, it actually so-called arrive at the IF. Again, this must be avoided because this may cause some IF distortion, and hence this must be avoided too. Next, RF to IF isolation, okay, which means that this isolation, this is much lower important as compared to the other two. So in general, RF to IF isolation is usually less of a problem than the LO signal. Why? Because the LO power level, in fact, they are significantly higher than the RF power drive. Basically, this is what we drive the mixer. This is what we actually obtain from the air. For example, for this case here, you can imagine that LO signal is many times as compared to the RF signal in terms of the signal strength. So therefore, because of this RF to IF isolation, it is actually has a lower importance as compared to the signal applied at the LO, which lead to the RF and also to the IF. Okay, so high isolation is also prevent unwanted interference and signal feed through. So this is the second parameter, isolation. Next will be 1 dB compression point. Okay, you probably hear this many times. What is actually 1 dB compression point? Before I come into that, let me explain what is actually linearity. Okay, so take a look on this diagram here. You can see that this straight line. Okay, so this is what we call linearity. This is what we desire, what we want, because this is actually predictable. Okay, so therefore, we want to design our mixer in this linearity region rather than the saturation region, which I'm going to explain soon. Okay, so basically the linearity actually describes how well the mixer actually handle the strong signal without any form of distortion. So what is actually 1 dB compression point? As I mentioned earlier on, this thing for a start, they can so-called provide the linearity, okay, which means that with certain input, it actually can achieve certain output. This thing is achievable until it reaches to a point that they can't cope this anymore, and in fact they become saturation, and because from here you can see that they starts to bend. Okay, so when they bend, okay, which is 1 dB lesser as compared to the linear power, this is what we know as 1 dB compression point. And typically for this point here, they are actually 6 dB below the LO power. So from here you can see that if we want to compute the power, okay, at the 1 dB compression point, it is roughly, okay, the power at the LO minus 6 dB. So in short, let me quickly explain this 1 dB compression point. In general, for a start, okay, let's say the amplifier or let's say the RF mixer, they can be increased in a nearly basis. But what happened here is basically once they reach the saturation, just like imagine this, you can increase your speed, okay, at the earlier stage. But however, at certain so-called stage, you probably cannot increase your speed anymore. This is what we know as saturation. And once saturation occur, let's say that they are actually 1 dB, okay, as compared to the linear state. This is what we know as 1 dB compression point. My next parameters will be on the linearity also, the third order intercept point. Okay, let me come to this diagram first. If you still remember, this is what we have discussed earlier on. This is what we call the linear line. And then this is what we call the 1 dB compression point. This is what we call the third order. Okay, so basically the intercept, okay, between the linear and also the IM3, this is what we know as the third order intercept point. Okay, so the third order intercept point actually measure the intermodulation distortion. Okay, so this is very critical, especially in a crowded RF environment. Okay, because okay, they actually determine how fast this thing actually decay. So hence, it is very critical in a very crowded RF environment. So in short, the higher the intercept point, the higher the dynamic range. So this is my next parameter, which is the third order intercept point. Before I continue, guys, this is very important to me. I hope you can support me by like this video. Guys, if you have learned something from this video, help me press the like button now. It's free and it's just a few seconds. For those who are new to this channel, and if you want to support me, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. The next parameters of RF mixer will be noise factor. Okay, so in fact, noise factor is equals to 10 log noise ratio. What is actually noise ratio? From here, you can see that it will be the signal to noise ratio at the input divided by the signal to noise ratio at the output. For mixer, okay, for example, for input will be at the RF port, as for the output will be at the IF port. So this is actually the equation for noise ratio. So what is actually this noise ratio and what is the role on the mixer? Okay, so usually it is in fact very close to conversion loss. For example, let's say for a passive mixer, basically the noise factor can be quantified by this equation, the conversion loss plus 0.5 dB. This is a very simple estimation of noise factor. Okay, so basically in short, noise factor actually indicate how much noise the mixer add to the signal. Okay, so like I mentioned earlier on, anything that you add, any component, in fact, you will also add some form of noise. So basically, this noise figure here actually indicate how much noise is actually contributed by the mixer to the original signal. So in short, the lower the noise figure, it will be better because less noise is actually introduced to the signal. This is closely related to conversion loss, as you can see from this equation, typically for a passive mixer. My next parameter will be dynamic range. What is actually dynamic range? Okay, so basically they are actually the input power range over which a mixer actually provides a useful operation. Let's take a look on this diagram in order to understand better. Okay, so basically from here you can see that this is actually the dynamic range. Why this is known as the dynamic range? Basically, imagine this. This is the zone that we can predict, the zone that is linearity. So after this point, it actually becomes the 1 dB compression point, which means that saturation, anything after saturation cannot be predicted. So therefore, we want to use the mixer at the so-called linear region as far as possible. So this is actually the definition of dynamic range. So in short, okay, the lower limit, okay, which is over here, the lower limit is actually determined by the noise floor. Okay, so basically this is actually the noise floor, while the upper limit, okay, so this is actually the upper limit, it is actually determined by the 1 dB compression point. So in short, the formula to calculate the dynamic range will be the input, okay, at the 1 dB compression point. Okay, so basically from here you can see that this will be the so-called 1 dB compression point. We need to know the input power, okay, at the 1 dB compression point minus away the input noise power. This will give us the dynamic range. Okay, so this range actually specifies the limits for the input power, and the higher the range, the better. So in short, the bigger the dynamic range, the better will be the mixer. So this is what you want to say. The range between the minimum detectable signal and also the maximum usable signal is also known as the dynamic range. Okay, so basically this is the minimum detectable signal. Okay, so anything just above the noise floor, this is known as the minimum detectable signal, and also the maximum usable signal, because after that it becomes saturation, which can be unpredictable. So basically this is the simple definition of dynamic range. So in short, the dynamic range is also depend on the noise figure and also linearity, as I explained early on. This is actually for the dynamic range. This will be my last slide for today's video. Okay, so intermodulation. Okay, so this intermodulation product, in fact, are unwanted signal that is actually created by the mixer. Let's take a look on this single tone intermodulation. So from here, you can see that there is only one tone. So therefore, this is known as single tone intermodulation. As for two-tone intermodulation, you can see that there are, in fact, two signals at the RF. So hence, this is known as two-tone intermodulation. Okay, so this intermodulation product actually depend on the LO power as well as the RF power. So in short, this is also known as the spur level or the spurious response. So mixer, in fact, they generate a lot of unwanted frequency. So basically, this is the general equation of this noise that is actually generated by the mixer. So in fact, this spur, they can interfere with the desired signal, and hence all this signal must be filtered. If you have learned something from this video, okay, I urge you to help me by like this video and subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.